All right. Hi, everybody. Continuing our PowerPoint slides of sort of using chemical informatics and computational tools as things that can help us do drug discovery. And I've added a couple more slides. I think now the slides will be done after we get through these remaining things. I have a couple case studies using some of our research, actually, in using computational tools. Well, today we're going to get into prediction of drug likeness using the Lipinski and Weber criteria. And before I use the computational tools, let's just show it one more time just to review what Lipinski and Weber criteria are. I'll run back up to when we talked about that, Lipinski rule of 5 versus Weber rules. Let me try to do that real quick. Yeah, okay, so we showed this example before, and I'm not gonna step through it all, but remember that we had kind of like a suboptimal drug with a pretty bad IC50, 2 micromolar, and that it had sort of good oral bioavailability predicted by Lipinski rules and Weber rules, and that's what we showed, maybe a couple lectures ago. And the Lipinski rules say that the hydrogen bond donors should be less than 5, hydrogen bond acceptors should be less than 10, molecular weight should be less than 500, C log P should be less than or equal to 5, and one violation is allowed. So in this case, one violation did occur, the C log P, but and overall is considered orally available. At least Lipinski would say so. And then the Weber rules say less than or equal to 10 rotatable bonds, so the 6 are predicted here, and PSA, polar surface area, should be less than 140. So all of this is kind of in agreement with the Lipinski and the Weber rules. Remember also that I kind of disagreed with how they counted rotatable bonds, and I think I'm doing it correctly. I'm not going to review that again, but yeah, in this case, I counted 7. On this right side molecule, I counted 12. The right side molecule was potent, IC50 roughly 1 nanomolar, but it had poor oral absorption that you can sort of predict using these parameters in Lipinski's rules and Weber rules. Okay, so now let's kind of move back into where we are in the PowerPoint and getting into the computational prediction of Lipinski's rule of 5 and the Weber rules. Okay, so I'm going to jump forward again. Where am I? Oops, sorry. Okay, so yeah, prediction of drug likeness, Lipinski and Weber criteria. The next thing we'll do is prediction of metabolism, phase 1 and phase 2 metabolism sites, like where on the molecule, and then the metabolite structures. So that'll review a little bit of what we did before. Hopefully you have not completely forgotten about metabolism. Okay, so Lipinski and Weber criteria. And we're going to use computer programs to sort of rapidly predict these things. Okay, so this tool, Mole Inspiration, it's a website we've mentioned before, has something called molecular properties determination tool. And this is the website, and we're going to actually try it out for a couple molecules and see how it predicts them. Yeah. Okay, so what we're going to do is demonstrate 3 classes of compounds in this little demo. Known orally available pharmaceuticals, so things that are predicted to probably be compliant with Lipinski rules and Weber rules. These preclinical pharmaceutical candidates, neuropeptide Y1 antagonists. That was actually what we just showed when I just reviewed it a second ago. So we have an idea that one of those should be orally available and the other should not. We'll do peptide-like pharmaceuticals, which generally speaking are bad oral available drugs, and we usually would administer them through intravenous methods. Okay, so let's try known oral pharmaceuticals, and we're given the little cheat sheet up here, Lipinski rules and Weber rules. That'll help us when we're determining these. I still think even the computer programs I don't think are necessarily calculating rotatable bonds correctly. So I think we can do it pretty good, and we'll practice this. But everything else is predicted fine. All right, so warfarin, Coumadin, which we mentioned in class before, is a blood clotting, anti-blood clotting drug, and it's used for people that have had surgery or various conditions, embolisms and things that you basically don't want blood clots because they can cause things like more embolisms or like stroke or things like that. Okay, so let's see. Okay, so I'm going to open up that mole inspiration tool, and then I need this smile string. And that was another point of this whole exercise, is we can use our smile strings, which we can get pretty easily. We saw that in the last lecture. But we can use smile strings to input a chemical structure for determination of drug likeness. Okay, so what I'm going to do first is I'm going to copy this to my clipboard. Okay, it's on the clipboard now, on the clipboard. Then I'm going to bring up mole inspiration, and over on the left you can see some of the various tools. We used previously the Galaxy 3D structure generator, and there's also calculation of molecular properties, and that's what we're going to use. Just for fun, let's try the 3D structure generator again. See if that works. All right, there's warfarin, generate 3D, and yeah, that we just figured out a 3D structure. I like the tubes. Yeah, and there it is, the coumarin structure with the benzene and there's a methyl ketone right there. Okay, so let's go back to mole inspiration, and we're going to do calculation of molecular properties and prediction of bioactivity. Okay, we're not going to do the prediction of bioactivity tool. We're just going to use molecular properties, which are what we use for Lipinski and Weber. All right, so paste in the smile string, and we're going to calculate properties. Okay, and so here we are. It gives us another 2D structure of it, and let's see if this compound agrees with the Lipinski rules, which are hydrogen bond donors and acceptors, less than 5 and 10 respectively. So for hydrogen bond donors, those are going to be the NOH-NH thing right there, right? OHs and NHs. Well, there's one OH. We see that right there, and so obviously that's less than 5. That's good. All right. So that rule is acceptable. How many hydrogen bond acceptors are there? Those are the other ones, N, O, N, so oxygens and nitrogens. Well, it looks like there should be 4. 1, 2, 3, 4. Yep, got 4. That looks like it's less than 10. Great. Okay. What about the molecular weight? It should be less than 500. Well, it calculates that for us. Okay, wonderful. So we're on our way to Lipinski compliance. 308 is less than 500. And let's see, what else do we have? C log P should be less than 5. Well, remember the mole inspiration tool, they don't really calculate C log P, they calculate their own variation of it, which they call mi log P or my log P. Okay, 3.03, which is, you know, fairly it's right in the middle of kind of where drugs should be. 3 is less than 5. All right, great. So we have no violations of the Lipinski rule. What about the Weber rules? Okay, rotatable bonds. I think I'm going to disagree with their calculation. I'm just going to measure. I'm going to calculate them myself because it's bonds between heavy atoms like a carbon and a carbon. So this is 1, 2, 3, 4, 5, and also carbon and oxygen. That's 6. So I see 6. They're seeing 4. And I'm going off the original definition. I just don't think the computer program is calculating this correctly. So rotatable bonds, I think we should just do this ourselves, right? 1, 2, 3, 4. 1, 2, 3, 4, 5, and 6. These are not rotatable bonds because they're parts of rings. Okay? All right, so, and then PSA is less than 140. Is calculating TPSA, topological polar surface area, is less than 67, so it's less than 140. So you could conclude that this drug is compliant with both Lipinski and Weber. Also remember with Lipinski, if it is in like out of compliance, 1 violation is allowed. All right. Okay, and the oral bioavailability, which means if you give this drug to a human or a rodent or something, how much of it is absorbed into their system? It's about 100%. So this is a highly orally bioavailable drug experimentally, and this matches kind of what Lipinski and Weber are saying. Okay, sulfamethoxazole or gantanol, which is one of these sulfa antibiotics, and it yeah, remember how these work. They interfere with PABA metabolism, and PABA was a folate source in bacteria, right? Okay, so let's take a look. We got a smiles string there. Let me copy that to the clipboard. Okay, copy. It's on. No, this is on the clipboard. So let's go back into mole inspiration. And to paste a new drug, I'll just go back. Paste. Get rid of the leading spaces. Okay, calculate properties. Okay, so here's this sulfa drug, antibiotic. All right, let's check Lipinski first. So my log P is 0.61, which is relatively polar. Remember, we kind of range from 0 to about 7, which is like around where cholesterol is in terms of greasiness. Okay, so C log P is less than 5. Great. Yeah, hydrogen bond donors and acceptors. Donors are 3. Great. Less than 5. Acceptors 6. Great. Less than 10. Less than or equal to 10. Molecular weight is right where we want it. Kind of, almost. We'll say 250. Great. Less than 500. And C log P, as we said. Yeah. So this is Lipinski compliant. What about the Weber rules for drug likeness? Well, rotatable bonds, which I'm not going to even look at theirs because I think it's going to be wrong. I see 1, 2, 3, 4, 5. They're calculating 3. Okay. Wait, 1, 2, 3, 4, 5. Yeah. Okay, but nevertheless, we are definitely well under the threshold, even if we use their calculation. PSA is less than or equal to 140. Let's see. Oh yeah, there's 98. Great. So all of this shows that we're compliant with the Lipinski framework and the Weber framework. Okay. And let's go back to the PowerPoint and see what the oral availability is. 85%. So this is considered a nice orally bioavailable drug. Okay, so now let's look at Lipitor, which is a cholesterol-lowering medication. And this has some chirality, so we have a couple chiral alcohols, and that's what these little @ signs refer to. Those are the chiral centers, and it defines the absolute chirality. Let me get this guy on the clipboard. Okay, this is on the clipboard. And let's open up mole inspiration again. Go back. Let's paste that smiles in there. I have some leading spaces. Let me see if it freaks out. And I'll try calculate properties. Okay, it did not freak out. And there it is, Lipitor. So let's take a look now at, let's take a look at the properties and if they, oops. Uh-oh, the screen's a little messed up. There we go, all right. Okay, so let's see, let's go down the list for Lipinski. Hydrogen bond donors less than or equal to 5. Well, it looks like we're good for the hydrogen bond donors, which are 4. Hydrogen bond acceptors are less than or equal to 10. Well, we're at 7 in this molecule. Looks like we're doing okay. Molecular weight should be less than 500. Okay, well, there we have a violation. We're at 558. Okay, and then C log P should be less than or equal to 5. Okay, well, we're in, now it looks like we have 2 violations. So we could technically say that this is maybe a problematic drug. It's interesting though because it is orally used, so we'll have to see what the oral availability is. But at least according to Lipinski, which is not like some perfect set of rules, it has exceptions. We are in violation of Lipinski twice. Okay, and then let's take a look at the Weber rules, and the rotatable bonds should be less than or equal to 10. The computer says 12. Let me see if I agree with 12. I see that one is 1. So it's between 2 heavy atoms, like an oxygen and a hydrogen, so or a carbon and oxygen, or carbon and carbon, etc. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I'm getting about 19 rotatable bonds, well over 10. So that looks like it's a problem with the Weber rules. And PSA, we are in compliance with the Weber rules because we're under 140. So we'll say we have basically 2 violations of Lipinski. All right. Okay, and then so it's funny because it is actually used as an oral drug, and it does work and it does what it needs to do, but the oral availability is 12%. So it kind of makes sense. So this sort of validates Lipinski's rule. It's not saying this cannot be used as an oral drug. It does kind of explain how given some of these properties, why we have such a low oral bioavailability. Okay? And yeah, the big violations were molecular weight and the C log P, which is a little on the greasy side, I guess, because above 5, gets greasier and greasier. Okay, great. I also think that the molecular weight, and why do they have this molecular weight cutoff in the Lipinski rules? I think as molecules get larger and larger, they have trouble getting through biological membranes. And if you take this orally and it gets absorbed in your intestines, the larger molecules start having problems. So that's why 500 is a pretty good cutoff. Okay. Okay. All right. So moving forward, let's show these research compounds that we mentioned before, the neuropeptide Y1 receptor antagonists, where we showed that one of them was kind of orally available but not potent, and the other one was very potent but not orally available. We'll see if we can agree with those experimental results. Okay, so this was that lead structure, poor potency, good availability. So what I'm going to do is copy the SMILE string. I determined the SMILE string for us. Let's get back into the mole inspiration tool, paste the SMILEs, calculate properties. Okay, Lipinski hydrogen bond donors are 0, so that's less than or equal to 5. Hydrogen bond acceptors are 3, which is less than or equal to 10. Molecular weight is 368. That's great. That's kind of where we want it. And C log P is above 5, so that is a single violation, and it calculates the violation there. So overall, this is fine with the Lipinski framework. And then the Weber rules, we'll do rotatable bonds in a second. PSA is definitely less than or equal to 140. It's 17. Good. Rotatable bonds. I'm going to do my own method again. 1, 2, 3, 4, 5, 6, 7. And they're getting 5. So either way, we're definitely Weber compliant. And again, this all kind of agrees with this being a nice orally available drug. Okay, they don't determine the oral bioavailability, but they do say that it is good. So we agree with it being good. Oh yeah, I changed my cursor back to yellow. So I'm always going to forget this until I start doing the PowerPoint, and then I'm going to change it for you guys. I think the yellow works really well here. Okay, and so then we have the optimized structure. So this has a very good IC50 in terms of inhibiting the receptor. 1 nanomolar will inhibit the receptor, but it has very bad oral bioavailability. So I have the, let's see, oh, there's the SMILEs. Let's copy that guy onto the clipboard, copy it, and then we'll see if our little tool will kind of agree with the bad bioavailability. Paste. Okay, calculate properties. Okay, so there's the structure. It looks like it's the same structure. Yes, they rotated things around a bit, but yep, that is the structure. Still amazing to me that a series of letters like this can easily map to a full molecule like this. That's the magic of SMILEs. Okay. All right, so let's check Lipinski first. All right, hydrogen bond donors, yeah, less than or equal to 5. Hydrogen bond acceptors are less than or equal to 10, so that's 6, good. Molecular weight is definitely above, so that's a violation, 591. And C log P or my log P is now actually, it's on the greasy side, so this is also going to be, it's above our cutoff of 5, and that's going to be kind of hard to absorb because if things get too greasy, they also have poor solubility and things like that. So that's why the cutoff of 5 is defined by Lipinski. And alrighty, so that we have 2 violations of Lipinski, right? And then let's look at the rotatable bonds. They say 11. Which would be a violation. Let me calculate them myself. So there's 1, These are not, because they're not rotatable. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I actually do agree this time with the computer program. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, it's actually, I get 12. Do it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So nevertheless, we're both of us, me and the computer program, both agree that we have too many rotatable bonds for the Weber rules. PSA is fine, so it's less than 140, so that's good. But you know, why do the rotatable bonds matter for the Weber rules? I think that since everything's kind of rotating, there's sort of a disorder, and that doesn't really lend its way to passing through a membrane or initially poking through a membrane. I should probably go read what Weber says about that, but nevertheless, rotatable bonds, it's one of his criteria, and this was demonstrated over a large number of compounds. Okay, so yeah, so we agree that now in this case, Lipinski and Weber are both out of compliance, and this matches the experimental result, which showed that this had bad oral bioavailability. Let's try a peptide-like pharmaceutical. So very peptide-like, and like we've said probably 1,000 times by now, that peptide drugs are bad or taken orally because they are not absorbed very well. This is vancomycin. I had the structure a few slides ago. I'm not going to show that. I don't really have space for it because it's a big structure. But here's the crazy smiles string. Let's copy that guy in and see. We'll calculate its oral. Well, it's if it favors Lipinski or Weber criteria. Okay, so I copied this onto the clipboard. Let's jump over. Here's the mole inspiration tool again. Go back. Calculate properties. Okay, so vancomycin should come up as a crazy. There's the crazy string. Yeah, there it is, vancomycin. And okay, so it's a sort of crazy cyclic peptide type structure with a lot of polar stuff on it, sugar, etc. So as you can probably imagine, this is going to be not very orally bioavailable. Well, let's look at Lipinski first. Hydrogen bond donors less than or equal to 5. Uh-oh, we got 21 of them. So that's a violation. How about hydrogen bond acceptors less than or equal to 10? Well, we got 33 of them now. Okay, well that's out of violation. Molecular weight should be less than 500. Okay, well we're at 1,449, so that's out of violation. C log P is maybe the one saving grace of vancomycin because it should be less than or equal to 5, and we are. But we do have 3 violations, so very Lipinski non-compliant. Let's check out Weber. I probably disagree with the rotatable bound count. I'm not going to count them here because it's going to take an hour. But certainly it should be 13, or definitely probably more than 13. And it is above the threshold. And then polar surface area is 530. Well, what's the cutoff? 140. Okay, so we're very clearly out of compliance of Lipinski and Weber. Okay, so this is pretty straightforward, right? Okay, so yes, the oral bioavailability is 5%. So it is actually a little bit active. It does pass into your body through the oral route. But it's also an incredibly expensive drug. So in order to get a good oral dose, you need a high dose of it, and so people don't do that. When this is used clinically, it's used as an intravenous injection. I think what I read is that the one situation where vancomycin is actually used orally is if it's treating like an intestinal bacterial infection, where it actually it doesn't need to be orally bioavailable because it just absorbs into your intestines and cures the infection that way. So in that case, oral bioavailability is not a big deal. Okay, so here's another one of these crazy molecules. This is vaguely related to vancomycin. I think it's a synthetic analog. And how do you know it's a synthetic analog? Well, things like chlorobenzenes are usually not found in drugs. And so this, I think, was kind of added to the structure to maybe affect its properties somehow. This is oritivancin, and I'll copy the SMILES string to the clipboard. I'm sure you can make a prediction on whether it is Lipinski or Weber compliant. Okay, I put this guy on the clipboard. Now I will step back, paste the SMILES, calculate properties. It actually takes a while to process it and figure out the structure. Okay, so now we have the crazy molecule in, and you can actually see the benzene, 2 benzenes and the chlorine now, right there. Let's make it bigger now. Okay, so let's look at the properties. Let's go down the list for Lipinski. Hydrogen bond donors less than or equal to 5. Yes, it's 22 now, so that's out of compliance. Hydrogen bond acceptors less than 10. Well, we're at 36. Molecular weight less than 500. Okay, well, that's not the case either. C log P is actually kind of closer to the cutoff now, but we are still in compliance. It's 4.8 versus 5. I think the addition of these kind of polar groups here maybe enhanced its lipophilicity a bit, made it a little more greasy, and that's why the C log P jumped relative to vancomycin. I don't know a ton about this drug, but there could be a reason they did that to maybe enhance its bioavailability a little bit. Nevertheless, it's still very Lipinski non-compliant. Weber rotatable bonds, well, now this is calculating 19. I don't have an exact number that using my process, which would take a long time, but we'll assume it's a big number. 19, all right, so that's out of compliance. PSA, yep, well above the 140 cutoff. Okay, cool. So this will be something you'll do on a homework assignment also. All right, so let's keep going. And yes, I didn't have an established oral bioavailability, but this is a drug that's administered IV. Prediction of metabolism. Prediction of metabolism. Okay. So, what we're going to do is look at the sites of metabolism, phase 1 and phase 2, and where on the molecule metabolism might occur, and then we're going to get into the possible phase 1 and phase 2 metabolite structures. So there's actually cool computer tools that allow us to do this. I can't review all of metabolism this second. We did, it all a couple lectures ago. But remember, phase 1 are like introducing a functional group onto a drug to maybe aid its excretion. And phase 2 metabolism kind of conjugates a molecule like glucuronic acid or glycine or glutamine, various things like that. Sulfate we saw, and that kind of also aids in excretion. Okay, so we'll use computer tools to actually predict this based on the established behavior of these metabolic enzymes. Okay, so we're going to use 2 different web tools to do this metabolism profiling. One is called the NERD server, which is New E-Resources for Drug Discovery. This is maintained, I guess, by the University of Hamburg in Germany. I think this is like the University of Technology or something in Prague in the Czech Republic. The University of Milano in Italy too. So this is a very nice international resource produced by these countries. We're also going to use something called Biotransformer, and this is a Canadian tool, and this is used maybe better for phase 2 metabolite structure prediction. This top tool is pretty good for certain things, but when it tries to predict phase 2 metabolite structures, I don't think it does it very well. So that's why we have two tools. They're both really easy, and we can use our smile strings for this. Okay, prediction of metabolism. First, we're going to do the nerd server. And this gives us there's kind of like 3 different things we can do. One, here's the URL. We'll jump there in a second. I'll get it on my clipboard. Okay, it says on the clipboard. So there's 3 kind of subtools in the nerd server that provide complementary information. One is it's called FAME3, which is the sites of phase 1 metabolism. So all it really does, without even describing the specific metabolites, it kind of gives you a probability distribution of the probability of various parts of the molecule being metabolized. And then FAME3 also has a tool for the sites of phase 2 metabolism, so places where metabolism might occur, or maybe maybe where a metabolite or where a conjugation might occur in phase 2. So where a glucuronic acid might attach or a sulfate. And then they also have another tool called GLORY, which is the predicted structure of metabolites. So this doesn't tell you the probability. It's more like, given a site, what might actually happen, what kind of a reaction, metabolic reaction might occur. So these are complementary. They give different information. And to really use this in a drug study, you kind of would look at the FAME3 and the results, and also the GLORY results. Okay. So let's check out FAME3 for phase 1 metabolism, and this is all the site of metabolism. All right, so let's let me see here. Let's open up web browser. Let's go to the nerd server. Uh-oh, didn't work. Why didn't it work? Let's see if I can find it. Here it is. Okay, let's try this again. Oh, okay. Well, it is. It's failing right now. I think it might be overloaded. I'm trying to get onto a website in Germany. This usually doesn't happen. What I'm going to do, I'll probably have to postpone just this part. Maybe I'll try it in the evening. And when you guys use it, you may have to try it in the evening. Okay, so I'm going to probably have to skip the nerd server stuff this second because the website's not working. Well, I'll post this, but maybe it'll be postponed a little bit, all right? That's surprising. It's worked multiple times for me. Okay, so we'll skip the nerd server stuff. What we're going to do ultimately is just try some different molecules, and yeah. Okay, so what I am going to do though, we'll try this biotransformer tool. Well, this is in Canada, so it should be a little bit closer. And And this is going to look at phase 2 metabolite structure prediction. And like where, given what we know about phase 2 metabolites and phase 2 metabolism, how they attach conjugate molecules onto something that's being metabolized, and this determines the structure of them, or it predicts it. Okay, so we can Google this, biotransformer.ca. Here we are, biotransformer.ca. There it is. Okay. All right. So this is we're on the website. This is on the Metabolics Innovation Center resource in Canada, and we're going to do a metabolism prediction, and we're going to do phase 2 transformation. So we're just going to look at phase 2 for this second. The nerd server thing works really well for phase 1, and we'll use that once we get it to work. I think probably in the evening. Okay. All right. So let's look at some phase 2 metabolite prediction. And Nerd Glory doesn't seem to predict phase 2 metabolite structures too well in my experimentation. So let's look at this molecule, 4-hydroxytamoxifen. Remember, tamoxifen itself is this is used as a drug for breast cancer. It's a estrogen receptor antagonist. But you might remember when we learned about this is well before we learned about metabolism, but I did mention that this molecule itself is not active. It's not an active drug. And so it is phase 1 metabolized in your liver to hydroxylate, I think, this position on this benzene, so you get this 4-hydroxytamoxifen. And this is the actual drug that has an effect in your in the estrogen receptor. Okay, so given this molecule, any predictions on phase 2 metabolism that you can think of? So phase 2 metabolism usually attaches something, and I guess almost always to like a nucleophilic atom in a molecule. Well, now that we have a hydroxy group on the drug, on this active metabolite, that might be a possibility. So you might think of like, what are the things that phase 2 metabolism attaches? Well, we learned about glucuronic acid is the weird sugar derivative. There's also, it's like a sugar with the carboxylic acid. Also like sulfate, things like that might be attached to this hydroxy group. Let's give it a shot. So here's a smile string. Okay, I just copied it to the clipboard. Okay, so now I just go down and stick in my smile string. It also says upload an SDF file. SDF files are a different tool for chemical structures. They actually also have you can do 3-dimensional structures in SDF files. We're probably not going to get into SDF files, but that's what it is. Okay, and it also has a prediction example. Let me try that first. I think that's, Tylenol, acetaminophen. So we'll just submit Tylenol just as an example first. It's going. Hopefully this tool doesn't break. Canada's closer than Germany. So this seems to be working. It says in progress. Okay, so now let's look at the structure of Tylenol real quick, just so we remember it. acetaminophen. Yeah, there's a structure. So this is a case also. This is actually probably a pretty good model for 4-hydroxytamoxifen because it's got a hydroxy group on a benzene, and the phase 2 metabolism you might predict are attaching those electrophilic things onto oxygen. So like glucuronic acid, maybe sulfate, things like that. Let's see. Okay, so the way to use this tool on the biotransformer website is we go down to select compound. So we put one compound in and it predicted 2 metabolites, and we do select compound, acetaminophen, and then you can see them. And what it's showing, the structures are in here. We just have to press the arrows. So aromatic glucuronidation, it predicts attachment of glucuronic acid. So yes, Tylenol could be glucuronidated on the phenol to make this product. These appear to be the same thing. They're both glucuronidation, and then it also predicts sulfonation. So so it predicts sulfonic acid formation on the oxygen. Okay. Yeah, and this also. Cool. So basically 2 metabolites, glucuronidation and sulfonation. Okay. So let's go back. I'm going to do the same thing, but I'm going to paste in my tamoxifen, 4-hydroxytamoxifen structure. Submit it. Okay, and it's predicting 3 metabolites now for this molecule, and I can select it. It just is calling it Q10372, and it's predicting glucuronidation of the oxygen, just kind of like Tylenol did. It's actually predicting glucuronidation of the tertiary aliphatic amine. So the amine, the nitrogen with 3 things on it, can be glucuronidated, and it's kind of a weird structure, but it's highly polar and it'll be pretty rapidly excreted. So you can, I think, hopefully you can see that the nitrogen on the amine, got glucuronidated. Okay, and then it's also predicting sulfonation of the phenol. So kind of the same way that Tylenol was also sulfonated on the phenol. Okay, so that was pretty cool. So that's an example of this the biotransformer tool. Let's try another one. So this is fusidic acid, or fusidin. It's an antibiotic, steroid type derivative. What kind of phase 2 metabolites might you predict, given the sort of nucleophilic nature of some of these atoms? You might predict, you can imagine maybe something happens to the carboxylic acid. There are phase 2 metabolites that might happen on carboxylic acids, I think, like glutamine formation and glycine. So these could be turned into amides. Also, you could maybe imagine one or both of these hydroxy groups could be phase 2 metabolized, maybe with a like a glucuronic acid or sulfate or something like that. Okay, so let's take this molecule, and conveniently shown as a smile string. Let me get the smile string on my clipboard. Okay, it's got the smile string. We will try the biotransformer tool in Canada. Back. Here's phase 2 metabolism prediction. Paste. Submit. All right, so it's predicting 2 metabolites, select compound, and it looks like it's pretty much assuming glucuronidation of the steroid hydroxy group, kind of the same way that the tamoxifen and acetaminophen were reacted, and then sulfonation at the same position. So it's not seeing it at this hydroxy group. There may be biological precedent for reaction on the steroid kind of leftmost ring, and maybe not on the other rings. And it could be maybe due to sterics or something. This may be a little more sterically open, this hydroxy group, right? Okay. All right. Interestingly, we're not seeing reaction on the carboxylic acid. If I was making a prediction, I'd probably say maybe glycine or glutamine could react with the carboxylic acid to make those sort of phase 2 metabolites. All right. Okay, cool. And yes, I'm writing that in the slide also. Maybe conjugation of the carboxylic acid could be predicted. But this tool is basically just saying, okay, well, this hydroxy group could have some stuff attached to it. Okay, let's see. Okay, so we are ready to get into the virtual screening, in silico synthesis, homology modeling, docking, and molecular dynamics section. What I'm going to do is actually, I'm going to wait on this, and I'm going to, maybe a little bit later in the night, I'm going to try the nerd server again, and just, I want to kind of finish all this other stuff before we move on. And so I'm going to pause this a bit, and then and either later I'm either gonna post what I just did, or I'm gonna throw in that little nerd server thing, which is the it's the sites of phase 1 and 2 metabolite formation, and also the nerd metabolite structure prediction. Okay, so I'm gonna pause for now. All right, I'll talk to you guys in a bit. Hey guys, so I still having a little trouble with that nerd server for metabolite prediction, and I emailed them to see if their server's down temporarily. I hope it's just a temporary thing, because I have a homework assignment ready for you, but I got to make sure that that server works and is reliable. And so I'm gonna wait on the homework assignment just a little bit more, and I'm also going to stop this lecture now, and just so I can post it. And if it starts working tonight, I'll just record the lecture I was trying to record, but then I'll just roll that over till Thursday. Anyway, so yeah, we're going to move forward soon, and then hopefully I'll be able to give you guys that homework assignment. I just want to make sure this nerd server thing is working reliably before I post the homework. Okay, see ya.